You type in an exact 11-character URL, G2Z4SM6WPI, into your browser and hit the click button. The video plays instantly. We usually treat digital video as a weightless abstraction, as if we are summoning pure light from a void. But high-definition video files are mathematically massive. Moving them requires physical infrastructure constrained by the rigid laws of volume and distance. The internet manifests as a physical grid of glass threads buried under sidewalks and laid across the ocean floor, strictly governed by the speed of light. A single HD stream forces millions of bits per second to squeeze through physical conduits thinner than a human hair. If 10 million people requested that much data from a single server in California at the same time, the volume would choke those microscopic pipes. Standard server models suggest that clicking that video link should trigger a cascading network failure. Preventing that collapse requires a global engineering pivot that moves the data before the request even begins. We tend to imagine our data streaming straight from centralized corporate headquarters directly to our devices. But physical distance creates lag. When light has to travel 3,000 miles through glass, the delay makes seamless high-definition streaming impossible. Engineers solved this by prioritizing geography over pure computing power. They built content delivery networks, or CDNs. CDNs are heavy, anonymous data centers fortified with massive power substations. They are built right on the edge of major population centers. They operate using a system called caching. When a video spikes in traffic, the network copies the file overnight and drops it into these localized server racks. Crossing the final distance to your house is a physical task. It takes manual labor to route these fiber optic lines underground, connecting the localized node directly to your street. The internet overcomes latency by physically moving the data into your neighborhood before you even decide to watch it. Physical proximity is only half the solution. If that localized server tried to push a complete HD movie file through your home Wi-Fi at once, your router would likely crash. To prevent a bottleneck, platforms use an algorithmic process called chunking. You never actually download a complete video file. The massive file is shattered into microsegments, each holding exactly 2 to 10 seconds of playback time. Your browser operates as a dispatcher, continuously requesting these chunks and stitching them together milliseconds ahead of the frames you are watching. This sequential race is fragile. A sudden bandwidth drop or simple signal interference can sever the connection. This graph illustrates adaptive bitrate streaming. When your local network speed drops, the host server intercepts the delivery queue in real time, swapping out a high-resolution chunk for a smaller, lower-quality block. This trade-off happens in the background. Visual quality is sacrificed for a few seconds to ensure the video never pauses to buffer. Passive viewing requires a high-speed negotiation between your router and a neighborhood server, repeating thousands of times per minute. If we pull back from the algorithms, the illusion of the weightless click takes over again. You don't feel the data centers caching files in your zip code, and you don't see the file shattering into 10-second chunks as it arrives. This entire planetary logistics chain evaluated your request, calculated the distance, and delivered the data in the 50 milliseconds it took to release the mouse button. A simple URL is a command prompt. Clicking it sets off an automated global logistics chain, moving data through thousands of miles of glass to hit your screen in under a second.